was to bring this to them in terms of trying to get you guys to address number sense by trying to manipulate values of x that make things work. And it kind of dawned on me about halfway through it. It kind of dawned on me about halfway through trying to do that you guys might be better, but I'm not going to take that chance. So we had this little bit of an issue about numbers and how things worked out all the time. Gentlemen, put the screens away, please. And what I want to do with you guys is kind of not do as an in-depth analysis as to why things work exactly the way they do, but kind of show you a generic way to make it work that's more efficient, okay? And that's what we left with in the second hour, so hopefully you guys won't get the blank stare as much as they did. So let's do this. When you first learned how to graph anything, let's say you had an equation y equals 3x minus 2. Before you learn anything about slope-intercept form or plotting zeros or doing anything like that, the very first thing you guys ever did, whether it was a linear function, a quadratic function, or anything, what you guys did was you always made a table set of values and picked numbers that made sense. You picked values of x on both sides of the y-axis, and you plotted it. You did -2, -1, 0, 1, and 2. You substituted in, you got ordered pairs, and you plotted. Okay? That's what you did over and over and over again until you learned shortcuts. It's the same exact kind of an idea when we get into working with roots. When I get into working with roots, I'm going to do the same basic principle here. I'm going to pick values of x that are simple to work with, that are easy on your brain. I'm going to pick perfect squares. So you have to remember then, what are your perfect squares? Well, perfect squares, if I'm picking values of x, well, the first one's 0, 1, 4, and 9. If I pick those values, I'm going to be able to take square roots easily, and I don't have to overthink it or try to do anything crazy. I know. So, here, grab a couple. Knock yourselves out. Here, grab a couple.
You want some?
Grab a couple, knock yourselves out. And send them all around here. I keep looking over and I think your hand's up. Like, oh, yeah, it's just this. So when we get into this idea of taking these values, when I'm doing this, I'm generating ordered pairs to plot. Okay? Square root of 0 is, square root of 1 is, square root of 4, and square root of 9. We stick with the first 4 real easy ones and try to go from there. Did you just poke yourself in the eye with that?
No, my eyes have been watering.
Oh. So, as you get into these things, your plotting here is what every single square root graph is going to look like in some shape or form. It starts at 0, it's increasing to the right and doing that. Okay? All of them have that same basic idea to them. Okay? What we're doing here is this is your most straightforward parent function. We talked a little bit about parent functions before. They are, we use them a ton, kind of starting now. And then we come back from break and we start talking about logarithms, exponential functions and things like that. Eventually we get to trigonometric functions. We're going to talk about parent functions again. And every single one of them has that a, h, and k value. Some value of a that increases the heights of how fast things are increasing or reflects them, makes them a negative, something along those lines. Directionality. An h and a k is a horizontal or a k is a vertical shift. Those things. I know it's stupid, but it works. So what we're going to look at is this. Today we're going to focus more on just the square root function Tomorrow we'll worry about the cube root one. When we talk about square root functions, it's the same basic idea. What we're always going to do is we're going to plot the parent function, which is your a root x, and then we're going to take those ordered pairs. There's a bunch of others that are mixed in. I think you guys might have some of them in your pieces of real quick. Please. What we're always going to do here is we're going to plot and do that. We're going to plot this parent function, which we're going to call a root x, and from that, each one of the ordered pairs that we generate from that, we're going to move them to h and k. And it's the same thing over and over and over again. We'll talk a little bit about domain and ranges as well. Okay? So if you go back and think of, yes, sir.
I was gonna ask if I like sit on the floor over there because I can't see very well.
Oh yeah, that's fine. You can sit anywhere. Here, let's do this. I'm about to sit on the floor. Here, switch it. Give more guys some room.
Problem solved right.
See? It's all good. Yes, it's like playing Tetris. Yes, it is. You want to bet? I have. I will put money on it. I'm not a betting man.
We're not focusing on this right now.
This is for Mr. Hirsch.
All right. So back to this. What I'm looking at here is identifying how you set this up and what happens with this h and k. Now remember, if it's x minus h, what I want to do here is identify what my a, h, and k is. From that, then I can start doing my parent function, and then I move it left or right, up and down. Remember, your h is moving you left and right, your k is moving you up and down. So here, what's your a? 3. This 3 is called a scalar. It's just a multiplier of how fast it's going to increase it or how slow it could increase it. If it's a negative, it would reflect it, things like that. Your h value here is what? -2. If my h value is -2, which direction is it going to move it? Left. So it's going to go left 2. And then my k value is -4, which means it's going to go what direction? Down how many? Down 4. So here's the really, really hard part. What are the 4 numbers that you always want to start with the square root? 0 and 9. So you start with those. 0, 1, 4, and 9, and you're going to use this as your parent function. We're going to use 3 root x as the parent function.
Yes, I was right.
No, you weren't.
Yes, I was. That's not what you were humming earlier.
Yes, it was.
No, it wasn't. It was. No. This
Yeah.
is still long.
No, it wasn't.
You're wrong.
No,
This is
ball.
fine.
He's like, no.
You're wrong.
Yeah, that's what I'm doing. Yeah. This is.
Yes, ma'am.
Are we always going to use 0, 1 scores?
Yeah, because they're perfect squares.
Yeah.
And then tomorrow when we do cube roots, tomorrow when we talk about cube roots, what are perfect cube roots? 0, 1, 8, 27. Same case. But basically what happens with cube roots, am I going to use 27 as a value of x very often for a 10 by 10 graph?
No.
I'm probably going to use just those 3. That's it. And then every cube root function is going to have the same basic shape, so it just mirrors the shape out. Okay. So here you go. Well, what's zero? What's the square root of 0?
0.
What's 3 times 0?
0.
Okay. What's the square root of 1? What's 3 times 1? What's the square root of 4? What's 2 times 3? What's the square root of 9? What's 3 times 3? 9. There's your parent function. Those are your ordered pairs. That's the parent function. That's what you start with. Always plot your a root x. Do that first because that gives you your 4 starting points. So 0, 1, 3, 4, 6, 9, 9. Do you guys, I'm trying to remember, I don't think we actually did a lot of parent function stuff before. So a parent function is a non-shifted graph. A parent function allows you to plot something with less work, but instead of trying to come up with numbers via number sense to get the shifted graph right away. So what happens here when you have what's called a parent function? Parent function's always gonna follow some pattern. A parent function, if you think of it, it's not a parent, it's just a space parent, like as in one parent function. Parents, like.
That's what I was hearing.
So, Jade, if you think about square root of x, the graphs are always going to do this.
Yeah.
X squared always does this.
Yeah.
X is always this, depending upon what the values of the scalars and stuff go.
X cubed is like that.
X cubed, right? X cubed does this. Sine of x
What is the sine of x?
is going to do this. Cosine of x is going to do this.
Do I need to know this?
Next time, we will.
No.
What's up?
Like wait, so these we're graphing right now, like with all the square roots, so it's only just this, it doesn't go down at all.
It's always going to be an increasing to the right because the bigger x gets, what's the value y going to be? Because what's the square root of 25? Square root of 36.
So does
Square
it
root.
just keep going up?
Yeah.
Wait, and then the ordinate 0, 0 doesn't go past that at all?
Do you take square root of a negative? No. Oh, I see what you did there. Oh. So what happens here when you're plotting this parent function, to help you move it to the actual function itself. So when you plot parent ones, it's a dotted line. Because it's just there to help you manipulate. Okay? Jared? Yeah. Okay? Yeah, it's already posted online. Should be. Wasn't? I thought I did it. Okay. So now, to each one of those 4 ordered pairs, what do I have to do to it?
Flip it.
No. What do I do? I'm not flipping anything. Shift it. I move it. The shift tells me move left, move down. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3. And there's your curve. There's your curve. I've taken that parent function, that a root x, plotted it with very easy numbers. To each of those initial points, I move them the h and the k. That's all it works out to be. You are shifting it from the original. That's what the h and k does. It's a horizontal and a vertical shift. Move them left and right, Move them up and down. And when you plot your official function, it's a solid line. So now if I look at my, excuse me, if I look at my graph that's solid, what's the smallest value of x that I have? -2. So my domain starts at -2, and is it increasing or decreasing? Increasing. So my domain of this graph now, my domain is all x values that are greater than or equal to -2. My range value, what's the small, where does my y value start at? At -4, is it increasing or decreasing? Increasing. So my range is going to be all y values that are greater than or equal to -4. That's how you find domain and ranges. Hey, what was your h and k? It's math. Okay? I need to walk up these aisles. There's too many people up the front rows nowadays. Let's try another one. Y equals -2 root quantity x minus 3 all plus 1. I will say this from time to time, the k value tends to float. The k value tends to float from either the back or the front. They can put it on either side. This is the exact same thing as seeing it as this, y equals 1 minus 2 root x minus 3. It does that sometimes if the a value is negative. It's not trying to scare you or anything like that, it's just showing that the commutative property of addition still holds true. That's all it's doing, okay? So once again, you start the problem the exact same way. I want you guys to get in the habit of what's your A, what's your H, and what's your K. The more you get accustomed to what these values represent, the easier it's going to be as we get into more complex graphing systems, specifically trigonometry, because we'll have stuff in there in terms of fractional amounts, okay? You're looking at, like, that's going to be horrible, but believe me, this becomes second nature after you get this down. It really does, because everything follows the same pattern, okay? What generic graph are you going to plot to start with? -2 square root x. What are the values of x you're going to choose from? 0, 1, 4, and 9. Once again, what's the square root of 0? 0. What's 0 times -2? 0. What's the square root of 1? What's 1 times -2? What's the square root of 4? 2. What's 2 times -2? What's the square root of 9? What's 3 times -2? -6. There's your initial set of ordered pairs. Yes, sir.
When it's like that, could you just like add 3 to each of the values on the left side? Since like when we shift it, anyway.
I see where you're going with that, because that's what's going to generate the shift values. That's the number sense part, and that's awesome. You want to do that? Go for it. By plotting the parent and then the shift, it's less taxing. It seems like it's an extra step, but if you got number, I tried to explain the whole number sense thing before and it blew up. That's why I said screw it. I'm not doing it with 12 hour. But that's fine. And you're right, because if you move it to 3, you get 3 minus 3 is 0, and then you just move that up 1, and you go from there. So I plot these 4 points. I have 0, Then it's 1, -2, so this now moves, since notice how my a value is negative, which meant it's reflected to the bottom half of the bottom part of the curve. 4, -4. What was it, 9, -6? It does that. To each of those points, which way do I move? I go right 3 and up 1. And now you do that domain and range idea again. You do your domain and range after you have plotted the official function. What is the smallest value of x that you're allowed to have in this graph? 3. So your domain, x is, well, which way is it going? Is the value, are the x values increasing from 3 or is it decreasing from 3? It's increasing, good. So x is going to be greater than or equal to 3. Your range is your y values. What's the largest y value or the smallest y value you have here? It's 1, and then is it decreasing or increasing? Decreasing. So it's all the y values that are going to be smaller than or equal to 1, because it's moving downward. Yeah. Why is it 3, not -3? Because it is x minus h. That means h is 3. Remember we did ordered pairs, and the only other time we really kind of did a lot with the h's and k's was with conics. So it was a quantity x minus 2 and y plus 3 was at 2, -3. It was opposite signs always. Okay. Yep. Hey, Jim.
Can you go back over like the range and stuff? Like this is only like the shifted one that you're getting it off of?
Yeah.
Or, like so like it having to be less than or equal to 1, would it be so like it's just it has to be anything that's
The range is what are the possible y values?
yeah.
Range your the top, since this is decreasing from 1,
Uh-huh.
1 is the biggest y value you're
Yeah.
going to have, which means it's everything smaller than or equal to 1.
Oh, okay. So like
Okay? Now, earlier we kind of gasped at the idea of like, oh, what's your h and your k for your domain and range? Your domain's going to work for your h value. Your range is only going to work by watching this sign here. The other one a second ago, it was -4 and up because your a value was positive. Here it's 1 and down, 1 and below because the a value is negative. If this was positive, it would have been 1 and up. So that's what you have to be careful with. Right? Does this change if the a value has a fraction on it? No. Could you fudge like a half or 3 halves or 9/2 if you had to? Yeah. Could you still count a fractional amount if you had to? It's the same stuff. Only if you had to. Now, if you didn't want to, but you had to, could you still do it? I don't know. If you have to. Then you didn't have to. Yes, ma'am.
so what would they like if we have this like a homework question like how would they ask it? Like would we know that
It's going to say, it's just going to say this, graph y equals 4 root x plus 3 minus 7. State the domain and range.
Okay.
That's all I'm doing with this right now, okay?
We're good.
Do you need to graph?
What's that?
So,
Yeah, I want you to graph this, but when you graph it, I want you to graph it via parent and shift. Because you're not wrong, but you're going to have to trust me. There's a reason why I want you guys to get accustomed to parent graphs. Because when we do get to y equals 2 sine of x minus pi over 2
you're gonna do that this year?
plus 4. Yeah. There's a reason as to why I want you to be able to graph a parent function out of this because you don't want to come up with sign values off the top of your head because it's going to be a pain in the butt. But as we get into this, knowing that every sign function has an a value that starts and stops at 1, -1, this just doubles it. It's got to go breakpoints. It starts at 0, it ends at pi, crosses at 0. It'll do that, and you'll be able to shift it off of that by constricting it and moving it up and around. But it comes from the idea of understanding how do you start with basic, and then how do you move it via those breakpoints. Because you'll be able to find these breakpoints, because I'm going to show you guys how all of this relates to ordered pairs off a unit circle. And you won't be using the calculator for about a month and a half.
Nice.
Okay? I had a couple kids in here that are in pre-calc right now. They're doing the same stuff. And they're going, oh yeah, that's why you did that. So, yes, sir.
Looks like we said 25 inches times X minus.
Yes, that's exactly what I did. Good work. It's the middle of December. You can't understand my chicken scratch yet?
What is that? Oh, it's an S.
Anyway, this is 6-8 in the book. I forgot what page it was. The 17. You know what? I did this for second hour. I actually just wrote down the problem number so you don't have to try to do 15 clicks to freedom. Page 418. The new one.
And we're just doing it all in graphs.
Yeah, I have six graphs for you. This is new book.
Should you just do it on this graph?
Yeah, that's what I give you. There's method behind my madness. Shut up.
So do you also want us to come up with the domain?
Yeah, it doesn't say to, but I want you guys to do domain and range with this also, okay?
Yep.
It's a good habit to get into.
So just write it like above the graph?
Yeah, that's fine.
And so we're just doing the same thing that we were doing before.
Yes, ma'am.
And I tried to make it.
Are you handing out like a final statement?
Bless you.
That we're gonna get before we leave?
I'm trying to get to it. I've been working on writing your test. If not, I will have the.
Oh, don't worry about it. You don't have to do that.
If not, it'll all be posted through here pretty soon.
Okay.
Those are the 6. That way, if you don't want to go ahead and 15 click the freedom, by all means, you can use this thing called a phone and probably take a picture of it. 0 and 0.
I'm literally gonna die.
Don't do that. It's annoying. So
I've been injured. I've been trying
what I've done, I actually have already posted through, and you guys might have checked your email. I already emailed you a copy of some review stuff for radical things. You get a good laugh on that one?
Yeah.
I already had a parent email me back with this is going to be awesome. So I always find that humorous. It wasn't your mom, no. I haven't checked my email recently though, so I'm sure I'll hear about it soon enough.
Why is it gonna be awesome?
You read your emails. That means you guys have to actually log into your school account from time to time and check your email. I know it's rare that. Well, there's a lot more in the daily announcement than besides just what they say. Because the daily announcements technically are like 3 pages, 4 pages long, but they only spend about 30 seconds talking about a few of them. So now that made me feel bad because the math team was in the daily announcements that were online, and you just dissed the math team.
I did not.
You did.
How dare you?
Don't act like Nick's the only one that disses the math.
Shut up. Hurt my feelings. Hey, does somebody want to let her back in or no? All right.